and I'm going to turn to our first speaker, John Porter. John is an internationally known agroecological scientist with an expertise in ecosystem services in agroecosystems. He comes to us from Montpellier, France, where he serves multiple roles, including a consultant on the One Planet Fellowship Program at the University of Montpellier and the Mediterranean Agronomic Institute. He also is an emeritus professor from the University of Copenhagen. John, I look forward to your talk.
Thank you very much indeed, and I hope everybody can hear me. It's certainly a long way to shout from Montpellier to New York, but I hope it's getting through on the internet. Thank you very much for the invitation. I was really touched and proud to be invited to something which is organized by the National Academy of Sciences. This is really a great honor for me. And I was asked to make my declarations, and so I've done these on the front page here. Christy mentioned Copenhagen, and also a member of the Greenwich University in the UK. I worked as a coordinating lead author for the IPCC fifth assessment and the chapter on food security, and a review editor for other IPCC productions. And also I sit on the INRA, the Institut National de Recherche Agronomique Science Council, which is like the USDA Science Council in France. These are both pro bono, but as a result of that, they made me a knight here in France. So I'm very proud to be a French Knight of Chevalier, as they call it here. And I'm an European Commission consultant, and my group and we've won a number of international and national prizes. I have the title of my talk is Resiliency Within Complex Dynamic Systems, and the thing about complexity is how do you tell it in a simple way? And so this is what I'm going to be trying to do, and I'm basically going to be talking about robustness, complexity, resilience, and efficiency. Those are the three elements, I think, which are really important for food systems for the 21st century. So if I could have the next slide. Yes, I think many people have said this in a different way, but we have Dickens's book, A Tale of Two Cities, and we are in a sense in a tale of two futures. And I think it's true to say that we live in the best of times at the moment. I remember my grandfather, he used to work on the docks in Liverpool and died at the age of 39 from asbestosis. We will not hopefully have to endure that much longer. But in a sense, we also live in the worst of times, because we are expecting this best of times to continue forever. And that is one of the big questions that we have to deal with in this particular time of history we are. And I believe that humans have a possibility of a really great future, but we have a very, very, very big problem to overcome, and that is global overheating leading to extreme climate change. One of the things which is really important when you're talking about climate change is the differences between things which are relative and things which are absolute. So something which is relative means, for example, the amount of emissions per unit energy, for example. These are relatives. This is improvements in efficiency are often expressed in relative terms. But absolutes would be things like what is the total amount of emissions of greenhouse gases into the atmosphere. And what I would say here is that one can improve the efficiency of fossil fuels and produce food more efficiently. But this does not necessarily mean that greenhouse gas emissions are reduced. And the reason for that is that really emissions are a combination of production and consumption. So this is looking at how one moves from a relative efficiency where we say we want more from less, to a system where maybe we say we need enough from less, because that is where we're thinking about also consumption as well. And improving efficiency does give you more from less, but still increases emissions. I just said that in another way. And improving efficiency and limiting consumption gives you enough from less and also limits emissions. And I think one of the things that we have to think about, we've been talking a lot about the food system since the Second World War. And we have to also bear in mind that the current economic system was also an invention of something which happened after the Second World War. It was mainly by John Maynard Keynes and Harry Smith here in the United States. And my feeling is that as we think about moving out of the food system we've had from the Second World War, I think we very seriously have to think if the economic system which we've had since the Second World War, which I would freely admit has been a fantastic success, is really the economic system that we need for the 21st century. So I came up with 4 hypotheses, which I hope maybe can be tested in a scientifically rigorous way. And I was intrigued by I've just read the biography of John Maynard Keynes, and one of the points he makes is, he says, when the facts change, I change my mind. And then he says, what do you do? So this is challenging us, if the facts change, that we need to think about how to change our mind. So my 4 hypotheses are that more from less does not lead to increased robustness, and that system redundancy is a good thing. I think there's plenty of examples of that, particularly, for instance, in the current pandemic and the way that different countries have dealt with the pandemic. I think of Germany, in comparison, say, between Germany and the UK. Germany has about the same population as the UK, but they've had about 1/5 of the deaths in Germany that has been happening in the UK as a result of the COVID-19 pandemic. Increased complexity can and also cannot lead to increased robustness and resilience. If you make systems more complex, they can have more robustness and resilience, but if you make them over complex, then that can mean that they lose this robustness and resilience. It's all about, in that sense, about a signal, how well a signal goes through the system and gives a signal for things which may have to change. I think it's clear that decreased robustness leads actually to decreased efficiencies. I think that is very clear. If you think of the COVID virus epidemic in different countries. And conversely, increased robustness leads to increased efficiency and resilience. So those are 4 hypotheses which I think are relevant if you want to talk about resiliency in complex dynamic systems. And if we think about greenhouse gas emissions, then this is a very simple, it's actually an identity, it's actually not an equation. Identity, but this was something which was developed by a man called Kaya, a Japanese man called Kaya. And he showed that you could calculate greenhouse gas emissions by saying how many greenhouse gas emissions there were per unit energy a country used, how much energy per gross domestic product, how much gross domestic product per population, and the level of the population. And basically what has happened in many economies, particularly Western economies over time, has been that the greenhouse gas emissions per unit energy have decreased as we've moved away from things like oil to methane and other sources of fuel which have higher heat content values. Energy per GDP has also often decreased, but what has really increased is GDP per population. The GDP per population has increased by about twice as fast since the Second World War as the other 2 production efficiencies have decreased. And that relative and total greenhouse gas emissions really just applies to the economic and energy sector. It doesn't apply to the agriculture and land use sector. And because of that, I actually wrote an equivalent equation to try and do the agricultural greenhouse gas emissions, where we looked at what is the yield per area, how much energy does it cost to make that yield, what are the greenhouse gas emissions from that energy, and what is the area of production. And if you take this in a fuller form, you can see this is in a more expanded form done by a very clever PhD student called Henrik Benetson. And here we have the different elements in this equation, which allows us to calculate the greenhouse gas emissions from crop. We also have one for livestock as well. But the important thing here is you have all these different handles. These are like handles that you can move up and down to affect the amount of greenhouse gas emissions you get from a crop. The point is here that we can look at the emissions both per unit area, but also importantly per unit product. so that we have both of these product and both area and product in this identity equation. And we have published this. This was published in Global Change Biology, I think in 2016. And when you do this and you look historically, here is a graph going from 1970 to almost the present day. And these are the calculations that have been made on the basis of the Kaya-Porter identity. And you can see that if you look at the lines below the value of 1 here, yes, here we are. So these are the values of 1, and you can see that some things are actually going better than they were. They've been improving. So the greenhouse gas emissions from soil per produced unit have actually been falling over time. The greenhouse gas emissions per produced unit have also been falling over time. And this is really not because the greenhouse gas emissions have been falling, but because the production has been increasing. And you can see that what is really causing the problem, if you like, is the greenhouse gas energy, how much energy is used per produced unit. And this then leads to this increase in the total greenhouse gas emissions from crops over time. So we can look at, from this, we can look at emissions per produced crop, and we can look at emissions per produced crop area. And this idea can also be expanded if you're thinking about the complex systems of crop production, to look at how resource use efficiencies interact. There are basically 3 resource use efficiencies. There is efficiency with which plants and crops use radiation. This is called a radiation use efficiency. There is efficiencies with which crops use water use. This is water use efficiency. And the final one would be how they use nutrients. What is the nutrient use efficiency? And those are defined basically in terms of, radiation use efficiency is how much dry matter you produce in a crop for a given amount of intercepted radiation. And water use, as a parallel, is how much you produce per unit of water that you've used. And one of the points, I think, and this is why this is the idea of a complex system, is that traditionally people have looked at these efficiencies as isolated efficiencies. And many of the computer simulation models which have been used in IPCC and other organizations to look at the effects of greenhouse gases and lack of water and changes in nutrition and these kind of things, have basically looked at these efficiencies as isolated efficiencies, but in fact they interact. And if you look at the top, this line here in the A, the yield per evapotranspiration, you can actually draw a little figure down here where you can look at each of these efficiencies in the different quadrants of the graph here. So here we have the graph which shows, or here we have the quadrant which shows the relationship between yield and evapotranspiration. This is number 1. And here we have the relationship between yield and intercepted radiation. So this is the radiation use efficiency. This would be the upper limit. Here we have the relationship between how much radiation is intercepted and how much nitrogen is taken up. And that will, of course, reach an upper limit as well, because at some point you can only take so much nitrogen up. And this is likely to have a slightly curvilinear response. And the 4th quadrant in this analysis, which I think is a very new analysis, is what the relationship is between the crop nitrogen uptake and the evapotranspiration. And the point I'm trying to make here is that you, given this framework, you can start to explore some of the complexities in the dynamic system of actually how crops grow in the field. And we've developed this together with colleagues in Lincoln in New Zealand. And they have produced a tool that they now take around with farmers, and they start to talk to farmers about these efficiencies and how they interact. The evidence for their interaction is taken from an experiment. There are other experiments. We heard from Cynthia Rosenzweig this morning about AGNIP, and there's a very beautiful experiment that AGNIP has got down in Arizona. Bruce Kimball, the US Department of Energy funded that. But this is an experiment from New Zealand, from a maize crop in New Zealand. And basically it's showing experimental results about how the nutrient use efficiency interacts with the water use efficiency. And so you can see here, and this is for a non-irrigated crop, and this is for irrigated crops. So you can see here that if you have irrigated crops, they have different relationships between the water use efficiency and the nitrogen use efficiency. And so the point I would really try to make here is that simulation models, this is a very good test data for simulation models. And I think more needs to be done about how simulation models deal with these kind of interactions between crops. One thing I think this idea of looking at these identities leads to is a way of connecting wealth, health, consumption, and greenhouse gas emissions, and then looking at the trade-offs between them. I haven't actually done this, but it would be a very interesting project, I think, to do. Here we have the Kaya identity, which we saw before about energy emissions. Here is the agricultural emissions. But you can also write an identity which talks about how much demand there is for food. Animal protein divided by total protein, what proportion, what was the ratio between total protein and calories, calorie per capita times population. And you can see that population would appear in a couple of these, and you could write other ones as well. But this would allow us to look at the interactions and also the trade-offs between these different factors which are important in wealth, health, consumption, and greenhouse gas emissions. The final thing that I want to talk about is the idea of linear and circular food systems. And these figures actually come from H.T. Odum's work. I think H.T. Odum's work as an ecologist has been very, very undervalued. It's been rather kind of sneered at because of some of the things he was into. But I think it's worthwhile really looking at what H.T. Odum and the Odum people down in Florida really got into. So here we have a linear system where we have an expected production maybe of 100% of, this is the expected production. And by the time we've gone through this process, we may have lost 50% of that or with these different losses. And these are losses which basically end up as waste at the moment. And one contrasts that really with a circular system where what you're trying to do is minimize the losses in the cycle and also then recycling as much as possible back into the system. So you're trying to develop as far as possible. I don't think it's possible to do it completely 100%, but you're trying to do it as well as possible. And I think one of the interesting things about a line and a circle is that a circle allows you to look at more interactions. I mean, basically you draw a circle on the basis of multiplying things together. You draw a line on the basis of adding things together. And I think it's very interesting to think about how you can introduce more interactions in a circular system than you can in a linear system. So here in Montpellier in 2019, we had an advanced research institute. We were looking at circular food systems, and these were the conclusions we came from. Basically, they were done by plant biomass is the basic building block of food and should be used first by humans. We need to avoid food and resource losses and waste. Byproducts from food production, processing, consumption should be recycled back into the food system. And we should use animals for what they are good at, which is a lot of the time about providing nutrition, like providing protein and milk. And this is milk and things like dairy products are very important for young children. They're very important for young women, pregnant women, and these kind of things. So this is very important. So I come back to my 4 hypotheses and put them forward as something which can be tested, I think, in terms of trying to look at resiliency and robustness in complex dynamic systems. And the final thing, I go back to this point I made at the beginning, and this is a quote from The Economist: capitalism must up its game. It was really talking about climate change. Capitalism must up its game. orthodox market economics have been useless in the current. And I think we need to think, if we're going to think about how we revise the food system, then we at the same time, we could not do this, I don't think, until we have an economic system which values the things on which the food system is based. So I personally have been through a process of saying, have I got enough? How can I use less? We have a program in Denmark where our food now is delivered by a company which delivers food to us every week, and it's very nice because you get the recipes and it's good fun and you can have fun making the food. And so there are ways in which I think we can think about how we can perhaps use less and make our lives a little simpler. A robust, flexible, and resilient and efficient food system in society needs both insurance and assurance. And my final thing is a question. How comfortable do we actually feel at present? How comfortable do we feel with the way that the world is going at present? And I ask that question because people only really start to do things when they feel uncomfortable. If we feel comfortable, then we can just continue with what we're doing. But if we're starting to feel uncomfortable, that's the time when we start to actually make changes. And so the question is, how comfortable do we actually feel at present? Thank you.
Thank you, John. That was really an excellent overview of complexity in the food system. I'd like to start off with a question on one of the themes that you talked about, was this tension between redundancy and efficiency. And there's been a real effort over the last several decades to move to more efficient systems. And we've seen, not just in the food system, but in many other systems with COVID-19, that losing redundancy had consequences that were most unfortunate, shall we say? And where do you see where we collectively need to increase some redundancy in the food system so that we can increase the resilience going forward?
To increase the robustness, well, I think if you're thinking about it as a complex system, I think we need to think about the diversity of the food that we eat and the balance between the things that we eat. I mean, I think we have to think of the food system not just as a way of providing food, but as someone said earlier on, and we heard this morning, I mean, it's basically a very important component in people's health. And you know, there are many interactions with the pandemic as well. I mean, the evidence from the UK and other places has been that people who are overweight are more susceptible to these things. So I think maintaining a diversity is one at the production end, I think, is really important. And I think also as well, I mean, what are we expecting to happen out of climate change? What means is society going to use to deal not just with the production of food, but also with the transport and distribution of food? And I think in that case, the robustness comes again from a diversity, from different ways of organizing food systems. I mean, I think there's a great research possibilities here. I have a very good friend at Oxford, John Ingram, and he and other people, and we also did this for capital cities around the world. We looked at the food systems of capital cities. And for example, Canberra is pretty self-sufficient, pretty food self-sufficient, but Tokyo, boy, they're susceptible to problems in the food system. So I think it's really about following the complexity, introducing more complexity into the food system, I think would be what my sort of capture of what I'm trying to say.
Well, that's great. Thank you very much. And I think in the interest of time, we'll move on.